Okay. So today I will talk about analytic torsion. So one second. Okay. Analytic torsion. So what is analytic torsion? Analytic torsion is basically a analytic invariant of a manifold, which happens to be a topological invariant, which is more subtle than homology. So basically, is a metric invariant of so metric invariant of the manifold by definition. But there is a theorem by Cheeger and Muller, and this basically says this says that this analytic torsion is actually a topological invariant. So okay, and this topological invariant is was defined before analytic torsion was defined, and it is called this is called Rademeister torsion. So this Rademeister torsion initially was defined to distinguish between length spaces, which are homotopic but are not homeomorphic. So So since these two length spaces will be homotopic, they will have all the same homology, cohomology, whatever groups, but they happen to be non-homeomorphic. So to distinguish them, you need to capture something different from the chain complex, and that is what the Rademeister torsion captures. It is something a bit more than homology. And the point here is this topological invariant has a analytic formula as well. So you can give a metric and you can define something, and it happens to be equal to that. Independent, it will be independent of all the metrics you defined. Okay. So I will only talk about analytic torsion this talk. The topological torsion is actually easy to define, but the equality between them is a long theorem. Okay, so to define the analytic torsion, first of all, I will need Riemannian metrics. So I'll just briefly tell what a Riemannian metric is. So given a manifold M, let's say of dimension n, a Riemannian metric G will be an inner product so it will be an inner product on the tangent space of M at each point. So at each point, I will get a GP, and this will be, this will take two vectors, and it will be an inner product. And basically, it will be a positive definite inner product and whatnot. And this will vary smoothly based on P. So if you change P, it will vary smoothly. So in some sense, so. the okay, so there are many ways to say this. So inner products can be given by matrices locally, and you will just ask locally that matrix is made of smooth entries. So that is a Riemannian metric. So it's just inner products on each of your tangent spaces. So this helps you it allows you to measure lengths in tangent spaces and angles. And there is a legit metric defined on the manifold using the same thing. So there is also actually a metric. Okay, so that's a Riemannian manifold. Then we also need the de Rham complex. So de Rham complex is basically, so let M be a closed N manifold. By omega I will denote smooth I forms. Okay, so omega I will denote smooth forms on the manifold, and there is a natural exterior derivative. There is exterior derivative d such that we'll get a complex like this. This is omega 0, omega 1, all the way up to omega n 0. And these will be just d maps here. These are different maps, but I'm just leaving out the di here. So this I actually have to say d0, d1, d2, but I will just forget those. Another property is d squared will be 0. Okay, so that's why this is a chain complex. And whenever you have d squared equal to 0, you can talk about homology or cohomology. So the cohomology here will be it is just kernel. Okay, let me just give the numbers 0, 1, 2. Okay. So kernel of image of Ti. So if you take this quotient, this will be the homology of your de Rham complex. So this will be denoted by Dr, I, and M. Okay, so by de Rham's theorem, this de Rham cohomology is isomorphic to the singular cohomology with real coefficients. Okay, so this is again a topological thing. It does not depend on the smooth structure or anything. Okay, so that is the de Rham complex. Next, so basically I'll just give a lot of definitions to define analytic torsion. So the next definition I need is hot star. For the de Rham complex, I did not need a Riemannian metric. So this is defined without the Riemannian metric. So all the complex here is defined without a Riemannian metric. But for hot star, I will need the metric. So using so mg is a closed manifold. Okay, so G was a inner product or a metric on the tangent space. By doing some kind of a duality, you can give the same metric on the cotangent space. So instead, I can just assume G is a metric on the cotangent space. So using G on TPM. Can give a metric on the cotangent space. Cotangent space is just the dual dual of the tangent space, and you can give a natural metric there. Or you can just take this as a definition that I'm giving a metric on the cotangent space for a Riemannian manifold. And these are basically one forms by definition. So at the point. So cotangent space is nothing but a bunch of one forms. So now I have an inner product on one forms. Now I'll just try to extend it to all k forms. So what you do is, so take two elements which are k forms. Take f, which looks like f1 wedge, f2 wedge, fk. It is a k form. And you can take g, which is g1 wedge, gk. So these are k forms. Okay, then what I want to do is, at each point, I want to define a metric on them, right? I want to define an inner product. I want to do this. So I also want to do this pointwise. So at a point P, this will be nothing but the determinant of this matrix, which is, so I already had a metric on omega 1. I will just do Fi Gj. Okay. And this will turn out to be a positive definite inner product on these k forms. And similarly, changing point will also change this smoothly. So basically we have a smoothly varying inner product on k forms. Okay. So that is good. Then since so this was a pointwise definition, what I could do is I could also integrate over the whole manifold to just get a number. So that is what I'll do next. So this gives, so this inner product will make omega k a Hilbert space, which will be take this one. By so this was a pointwise thing. I just integrate it over the whole manifold with the volume form. Right, so that'll just just give me a number, and that will be an inner product which I'll keep using. So that's an inner product. Now, what is the hot star? So hot star. What I want to define the hot star would be, it is taking k forms, and it will give me something which is n minus k forms. So example, on R4, let's say, what I want to do is, let's say I take the form dx1 wedge dx2, and I want to take the star of this. What I want this to give will be dx3 wedge dx4. So basically something that will complete the basis. This had dx1 dx2. I want, when you take a star, I want it to give me the remaining things which it does not have. Similarly, if I want to take the star of 1, that will be, because 1 has nothing, it will have to give me everything. Right, so that is the goal of defining the hot star. It is basically to complete the missing basis of your forms. Okay, so how do I define it? For all, let's say, omega and eta, let's take k forms. I want to define the star such that I have this kind of a property. So what I want to do is, if I wedge omega and the star of eta, I want to get the volume form, just get the top form. And this will be kind of that something that takes care of cancellation or multiplication or coefficients. That's what this will take care of. If you just look at omega wedge star omega, this will be determinant of omega. So this will be the inner product of omega with omega. So that will be a positive number, and this will just be the volume form. So if it was a orthogonal or a vector of norm 1, this would be 1, and you'll get the volume form. So basically that is the requirement for the hot star, and that will be a pointwise thing, and it will be defined locally, and you can patch it up, and I'll not say more about that. So then what are the properties? So first property is it is kind of symmetric. So if I do this, it is the same as taking star first, then wedging with theta. Then second property is if you take star twice, it is almost an involution. It just misses that there is a minus sign coming out. Okay, so if I take star squared, I'll just get a negative sign to some power. Then finally, I also want that the inner product that I defined initially, or like here, this is just take the star, then wedge it with omega, and you integrate over the whole manifold M. Basically, that is the inner product I had defined. So there's a nice formula for the inner product here. Okay, so those are the things I need. Now that we have an inner product on the chain complex, I can talk about adjoints of the operator D. So I want to look at the formal adjoint. Or let's forget the word formal. Adjoint of D. So D was an operator, and I want to figure out what the adjoint of D is. So let's first take omega to be k minus 1 and eta to be k. What I want to look at is I want to look at this, and I want an operator which does this. Right, so I just want to understand what this operator is. Okay, let's just calculate what d omega eta is. This is from the formula we had. It was this integral. Using some property of the exterior derivative, this I can put the d from here. I can put the d from here to here, and it will just pull out a negative sign, and that will be just negative 1 to the k. Okay. 1 second. Yeah, negative 1 to the k omega wedge t star. Okay, so d was here, and it just moved to the other wedge. Okay. Now I'll just
so it is k or k plus 1.
Which one?
This last one,
It's this is k, I think, because this was omega was k. Sorry.
Oh,
omega was k minus 1, and there's a minus sign which comes by
right.
integration by parts. Yeah, so this is a minus. This is to the k, and what I'll do now is I'll introduce a star squared here. Basically, I'll just do minus 1 to the k omega wedge star squared this. Then oh, but I have to introduce a negative sign to the power of something here. It will be something. I won't write that. It's just too big for that. So there is some number there, minus 1 to the something. So if I pull that out together, it will be just integral minus 1 to the k omega wedge so star d star beta. Okay. Now if I just change bunch of few things together and write it in a different form, this will just be the inner product of omega, and it will be minus 1 to the n star d star beta. So this is just by definition. So when I write this inner product, this will be integral of this star, which is exactly this. Okay, so this is basically this becomes this, and the d star that I wanted is over here. So this is the d star that I wanted. So I have found the adjoint of d, which is minus 1 to the n times star d star. Okay, so this is the adjoint of d. I will call this del. Okay, so now what is the property of del, or I can just define this as del. So del, because of what's happening here, by this definition, it will just map k forms to k minus 1 forms. So it will just go 1 degree lower, and it will be mapping in the opposite direction. And I will also have that del squared will be 0, which can also be seen by doing square of this, because you'll get this squared. So star will cancel off, and d squared is 0. That's why this will be 0. So that is the del. Now that we have d and del, I can define the Hodge Laplacian. So the Hodge Laplacian, so Laplacian on k forms, we'll just take k forms to k forms, and it will be defined like this. So the 0 forms. So I had an operator d, which maps like this. D. Then using the Riemannian metric, we constructed a operator del, which goes like this. Del. Right, so the Laplacian will just be defined like this. You start somewhere, go forward and come back. Then you also go back and come forward, and just add them. That will be your Laplacian. So the Laplacian will just be defined as d del plus del d. Right, this is also nothing but d plus del whole square. Okay, so this this Laplacian is a second order partial differential equation. So partial differential operator. And it also is elliptic. Elliptic means it's almost invertible in some sense. Okay, are there any questions up to now?
So why it is so del k? I mean the last two equations del d del plus del d equals to this. I mean, so are you using del compose del equals to 0 or decompose d equals to 0? I think which
For
one?
this,
Yeah, for this.
you'll use both. So this will be nothing
Both.
but d squared plus del squared plus d del
Yeah.
del
Okay.
d. So these two both are 0. So
Oh, right, right,
yeah,
right.
these two are zero, so this is here.
Oh,
Again, I should also be saying there are different numbers here. So this is k plus 1.
yeah,
This is
I
also,
understood.
and this is k minus 1 and k or something. There are different numberings there, but it's just makes it easier if I write it like this. You should just be thinking of going like this and
Oh,
like this.
and you said that it is elliptic in some sense, that it is invertible. It means that a point-wise text, it has a matrix, and that matrix is invertible in that sense.
No, not in that sense. It's so
No,
basically
okay.
when
So
you do this,
so I'm saying that their coefficient matrix actually invertible in that sense.
oh, elliptic, yeah, elliptic means it's the matrix is invertible. But when I say what is the meaning of ellipticity, it means that this operator is almost invertible.
Almost
Okay.
invertible.
Almost, basically one thing you can think is this is Fredholm operator, which means the
Understood.
why it is not one-to-one, because the kernel is there, but it's a finite dimensional kernel, and what it misses out in the image is also finite dimensional. So just leaving out finite dimensional things from both sides will give you an invertible operator.
Leaving out means quotienting out, this kind of thing.
Yeah, quotienting out, or you can just orthogonally separate them and you
Oh,
forget. Yeah, just like leaving finite dimensional things, this is invertible, and which is something which will be used. Actually, I won't use it today, but that is an important property of being elliptic. Okay, any other question? Chat, I think, okay. Okay, so this operator is basically supposed to look locally like, so example, if you look at on Rn. So local picture for this will be Laplacian on. So if I just take omega 0, which is just C infinity functions of your manifold, Laplacian acting on the functions will be negative summation I put 1 to n del squared f by del xi squared. So you just take all the coordinate directions and you differentiate it twice and you put a negative sign. So that's just the usual Laplacian everyone works with on real Rn, and this is just generalizing that on manifolds. Yeah. Then what are the properties of this Laplacian? First thing will be this is positive semi-definite. Basically, if you look at Laplacian, if you look at this inner product, this is nothing but T del omega del d omega. And D was the adjoint of del, so I can just move it from here and make it a star when I move it to the other side. So this becomes del omega del omega. Similarly, on the other side, it will be this. So del is also the adjoint of T. It's just a dual thing. And you get this, and because the inner products was positive semi-definite, this will be greater than equal to 0. Let's call this star. Then we also have something called harmonic forms. So harmonic forms are just they are just the solutions of this PDE. So you just apply your operator and take 0, or it's just the kernel of your operator. Okay, I don't have to say anything. Right, so all omega such that this happens, that's your harmonic forms. And one property of this is if this is in fact 0, it will tell me that d del plus del, actually no, not this. This will actually tell me that this inner product, which I computed earlier, this has to be 0 because this was 0. But this, as we saw before, is nothing but d omega plus del omega. Now, since both these are positive or non-negative, both of them have to be 0. And both of them having to be 0 happens only when this is 0 and del omega is 0. So if you have a harmonic form, it will be closed. So d omega equal to 0 is closed and it will be co-closed. So del omega 0 will be co-closed. So in particular, since harmonic forms are closed, I can map this into the de Rham cohomology. So there's an inclusion map here. So all the harmonic forms, since they are closed, they will go and sit in the de Rham cohomology. And yeah, so this inclusion is there, and this inclusion, so this is a canonical inclusion. So I'll just write that canonical inclusion. This inclusion actually happens to be an isomorphism. So your harmonic forms, which I defined through some analytic PD solutions, happens to be equal to the cohomology of the it's a cohomology of your manifold. Okay, so that is the theorem by Hodge. So actually, this is called the Hodge decomposition. So all your omega of k forms, smooth k forms, they will split as image of D plus image of delta plus, so these are orthogonal direct sums plus your cohomology. So all smooth forms are decomposed in terms of either they are images of D, images of deltas, or they are in the harmonic forms. And this gives a immediate corollary that I is an isomorphism. Okay, so it is easy to see this implication. And this theorem can be proved in many ways. One way you can do it is by constructing an elliptic inverse. So you will construct some kind of an inverse for this, which will happen to be a pseudo differential operator, and which it will give you nice properties, and that will kind of tell you this. But that is for a different story. So basically, you can see this will imply this easily. So what we will have is the harmonic forms are basically giving you cohomology. Yeah, that's not something I will use, but that's something you should keep in mind. Okay, final property I need is since delta this Laplacian was a positive definite operator, is positive semi-definite, and it is also self-adjoint. I think these are more properties than I need, but these two happen, and there is a inverse which is a compact operator. So what happens to this is this will have a discrete spectrum. So Laplacian will have so it will have only point spectrum. So which means it just has eigenvalues. And no other thing to worry about. Eigenvalues, and all these eigenvalues, they will have finite multiplicity. Multiplicity, and they go off to infinity. Okay, so that is something I will need here. So this in particular will say that it's discrete and whatnot. So let me denote the spectrum.
So I have a question. The self-adjoint in sense of hot star sense, right?
In what sense?
Self-adjoint. So delta is self-adjoint. Del star equals to del. That you say? Or?
Yeah. So this I have
Oh,
this,
right.
right? I had the inner product on K form. So
Oh,
it is just
okay.
so this was, if I had written correctly, this should have been the star, but if you
Yes.
compute it, star will be equal to itself.
Okay.
So this is what I mean by.
I have a question. Do you mean the eigenvalues will go to infinity?
Yeah, all the sequence of eigenvalues will go off to infinity.
But don't we know that spectrum of a operator is a complex set, so it has to be bounded?
Yeah, this is not a bounded operator.
I see.
Yeah.
Okay.
Its inverse will be a compact operator, but this itself is not a bounded operator.
I see. Okay. Thank you.
This delta has a non-trivial kernel, right?
Yeah.
So what do you mean by the inverse of delta?
Yeah, that's what I was saying in the beginning. It's almost invertible, right? It will be a pseudo inverse, basically.
Okay.
Yeah. Yeah, it also has co-kernel, so you cannot do any.
Right.
Yeah. Okay. Okay. So anyway, so this was that. So spectrum. Let me just. So this is point spectrum. So let me just denote it by the sequence lambda I. I will go from 1 to infinity. And this sequence goes off to infinity. And I will also say ignore lambda equal to 0. So just forget all the 0 eigenvalues and take only the non-zero ones. So the 0 ones are just finitely many, so you can do that. And that basically counts the homology or cohomology. But we are throwing those off for the definition I need. So I want to define the analytic torsion. So what I want to do is, this is, okay, no. Just the number I want to define, it will look like determinant of. So basically I want to say take determinant of lambda 0, sorry, delta 0, delta 2, whatever, divided by determinant of delta 1, whatever. So an alternating determinant of your chain complex. Now, when I want to do this, the problems here will be what do I mean by the determinant of some operator? So determinant of an operator, let's say, if I define the determinant of this to be the product of the eigenvalues, lambda I, the problem with this is this will diverge to infinity. So this doesn't really make sense. So the way to go around it is you'll just define a regularized determinant in a different way. So to do that, first I'll define a zeta function of this lambda k. So take some complex number s, then define this zeta function to be summation I equal to 1 to infinity lambda I to the s. So this is why I ignored the 0 eigenvalues, because I don't want it to cause trouble here. So this is well, defined for some real part greater than some constant. Let me just say it like this. So this is actually a theorem. And this has a meromorphic extension to all of C and is at 0. So it is analytic at 0. So what I will do is I will define my determinant to be the derivative at 0. So if I just write this very in a wrong way. So this is something that is not true, but it just helps understand things. So if I took the derivative of this thing, what I will get is I will get I to this log of lambda I. Okay, then when I put 0, this is supposed to be equal to 1 to infinity log lambda I, which is kind of the product of lambda i's I wanted. Okay, this is not a true statement. Only if this was a finite thing, I could have done all these. But this kind of gives you the intuition of why we will define the regularized determinant in this way. So regularized determinant of this will be, so the log determinant prime. So this is, I'll denote this by the regularized determinant, will just be defined as take your zeta function, differentiate it, and take its value at 0. So now you have a determinant, and the Ray-Singer torsion, so the analytic torsion, which is actually defined by Ray-Singer. So this is basically defined as there's a half factor to make things nicer later on. But, it's just this. Okay. So yeah, this is actually the log of the Ray-Singer torsion, but that's all, not the important thing. So yeah, and this analytic torsion, for reasons you can see, because I ignored the cohomology, this captures something more than the cohomology of the complex, and this will be the Radmeister torsion, so it will actually help in distinguishing these length spaces. So this is in fact capturing something more than what cohomology was capturing. Okay, so I will stop here. Did anyone have any questions?